Greetings and salutations, magical chemists. Today we're going to talk about integrated rate laws. This is a second method that you can use to determine the reaction order with respect to a different reaction. To do that, you're going to need to graph things. Specifically, you're going to need to set time as your x-axis, and then you're going to make three different graphs. So you're going to graph the concentration of the reactant versus time. You're going to graph the natural log of the concentration of the reactant versus time, and the reciprocal of the concentration of the reactant versus time. When you compare the graphs, only one of the three should actually be a straight line, and that's the one you're looking for. That will tell you what is the order of the reaction with respect to that reactant. Luckily, if you write them in alphabetical order, it will tell you exactly what to do. So notice, concentration starts with a C, so that comes first. If the concentration versus time graph is the most linear, then this reaction is 0th order with respect to that reactant. But if it's the natural log, because that one starts with an N, that one comes next, well, in that case, it would be first order with respect to that particular reactant. And finally, if the reciprocal versus time is the most linear, well, in that case, the reaction is second order with respect to that particular reactant. And even better, once you find the graph which is most linear, you can find the rate constant by looking at the slope. For every single one, it turns out the absolute value of the slope is equal to the rate constant. Of course, that only works if you pick the correct graph. Because notice, two of the graphs, the one for the 0th order and the one for the first order, are actually negative slopes. So you would have to take the absolute value, aka the positive value, to get the rate constant. But of course, the second order one already is positive. So you are safe if you remember, just take the absolute value and you will always be able to find the slope. All right, so let's look at a beautiful summary of this information. So it gives you the order of the reaction, its rate law, the units for K, and what we call the integrated rate law. The integrated rate law is just the slope of the line that you get when you graph the most linear version. So for instance, 0th order, concentration versus time, that's the one that's going to give you a straight line. If you are looking at first order, well, remember, it's graphing the natural log that's going to give you a straight line. So in this case, the integrated rate law is for natural logs. Notice that all these is there's just a y equals mx plus b. This is a slope-intercept form of a line. Of course, for the last one, you are looking at reciprocals. Now, the formula chart will actually give you two out of these three equations. So they'll give you the one with the reciprocal and the natural log. They're not going to give you just the basic equation, but you really don't need this because frankly, it's just the whole, y equals mx plus b, where m is your slope and, b is your y-intercept and all that jazz. So this is just, straight up mathy math. So it is true they're not going to give you that one, but you can figure it out, so you're totally safe. It's just a way of finding the slope because, of course, you need the slope to find the rate constant. You will also notice they're giving you information about half-life. We're going to talk more about half-life shortly, but it's important to note that even though technically you can calculate the half-life, which is the time it takes for 1/2 of the reactants to be used up, so it's represented by T 1/2. You can calculate the half-life for any order, 0, first, second order, but only one of these orders is constant. It does not change regardless of the concentration of your reactant, and that would be the first order half-life. It turns out first order half-lives are the only ones that are AP tested, so they're going to give you that equation on the formula chart. There are other half-lives, and you can totally calculate them. Like this is a thing, this is totally a thing, but they're not going to show up on the AP test. Okay, now that we've got that beautiful summary of all that delicious information, let's go ahead and look one more time at the units for the rate constant, because we're always going to have to know the units for the rate constant regardless of how we figure out what the rate order is. So, the units of rate never change. Rate is always molarity divided by time. It's often molarity per second, but it's not always. Make sure you notice which unit of time is being used. You can use dimensional analysis like we did previously to figure out the units for k, and that will always work. But there is a handy-dandy equation that you can use. You would have to memorize it if you want it, but it is short and sweet if you want to use this to always figure out the units of k for a specific rate law. So first you have to figure out the overall order of the reaction. We call that P. It's just if you add up all the individual orders, then the units for your rate constant are always going to be molarity raised to the power of 1 minus the overall rate order, then times time to the -1, because that one's always going to be true. All right, so here's what we're going to do. We are going to determine the units for k for each of the following rate laws, but there was, of course, a mistake, so let's fix the mistake. I would like you to go ahead and make this one down to the very last one, make that one squared. Okay, so let's do one of these together, and then you will do the rest of these on your own because they're just that much fun. Okay, looking at number 1, we've got the rate is equal to the rate constant times the concentration of NO2. Well, you notice they didn't write anything with the concentration. There's no exponent, which means it's implied to be a number 1. So the overall order of this reaction is simply 1. Well, following our short little formula up above, you would plug this in, you'd be like, okay, well, I've got m to the power of 1 minus the overall rate order, which is just 1. 1 minus 1 times time, whatever the heck time we end up using, to the -1. Well, you notice 1 minus 1 is 0. And anything raised to the 0th power is just 1. So this whole thing just equals 1. Got a little messy there, but. So in this case, the units for k are simply time raised to the -1 power. Or if you're feeling like you just don't want a negative exponent in your life, you could say that this is 1 divided by time. All right, so go ahead and try these last 3 just for funsies. And when you're ready to check your answer, well, of course, unpause the video. All right, the second example was third order overall, which means the units of k are going to be m to the -2 times time to the -1, which is just 1 divided by molarity squared times time. All right, the next one. Well, in this case, this was a 0th order reaction. So the units of k are going to be exactly the same units of your rate, molarity divided by time. Last but not least, because we fixed this last one, it ended up being second order overall. So in that case, the units of k are 1 divided by molarity times time. That's it, short and sweet. Remember, this equation is just kind of a quick trick in case you want to use it, but it's never going to be given on the formula chart. So you either got to be able to figure out the dimensional analysis or remember this equation. All right, let's try some practice problems. It'll be amazing. So first, you're going to go ahead and try these problems on your own. Notice, there are 5 different possible choices. You're determining which one matches with which. All right, and when you're ready to check the answers, well, you know what to do. Okay, if you want something that is 0th order with respect to A, you want a reaction that doesn't have A at all. And there's only one reaction that doesn't show A at all, and that would be reaction E. Notice, this one is first order with respect to B, but it does not show any effect with the concentration of A. All right, the next one, we want something second order respect to A, but third order overall. Well, if it's second order with respect to A, third order overall, it must be second order for A, first order in B. So that one clearly is reaction D. And then last but not least, 0th order with respect to B, so no B at all, and second order overall, which means it must be second order with respect to A, right? Because it was 0th order with respect to B. So, hey, that one was answer choice B. All right, let's try a couple more together, and then you shall be free. All right, so 2 more practice problems. Again, try them on your own first, just because you're cool like that. And then, when you're ready to check your answer, unpause the video. Okay, if you were looking at number 4, hopefully you can see that there are some answer choices you can definitely cross out, because this is talking about integrated rate law. And in the integrated rate law, you're always graphing something. The something changes, but it's versus time. You are never, ever, ever, ever going to graph the reciprocal of time. So you can automatically say that B and E are never going to be the right answer to anything. So if you recall, you can figure out the order of the rate law, or the rate order with respect to the reactant, by looking at these in alphabetical order. So remember, concentration comes first. So if it's concentration versus time, that would be 0th order. And then natural log alphabetically comes next. So if it's natural log versus time, that's going to be linear. That would be a first order. But if it was the reciprocal, which is 1/x, then it would be second order. Well, in this case, they wanted to know, they were giving you this particular rate law, and this one means that it must be second order with respect to x. So the only correct answer choice here is C. Okay. The next one, number 5, we want to know what can affect the rate of a chemical reaction. Well, there are lots of things that can affect the rate of a chemical reaction, but remember, nothing to do with products. Products are not part of your rate law. So catalyst, temperature, reactant concentration, breaking up solid reactants, all of those things will definitely affect the rate. But screwing with the amount of products that exist, that'll affect equilibrium, but not the rate of the reaction. All right, we will spend more time practicing with the integrated rate law next class, but you are now ready to leap forward into our next video about colorimetry. Yes, not calorimetry, colorimetry. So you can be ready for the Crystal Violet Lab. Thank you for playing, and I'll see you in the next video.